All right, friends, students. In this video, I will be discussing about the problem known as particle in one-dimensional box, and this problem, solving this problem, explains us that how applying boundary conditions and using normalization in a particular problem automatically lead us to calculate the wave function. So, to make you familiar with the problem, we have a one-dimensional box. This one-dimensional box has infinitely hard walls. Okay, in real world we don't have infinitely hard real walls, but we are assuming here infinitely hard walls, so that the wave function at the boundaries of this problem boil down to zero. And then you have a particle, and this particle has constant potential energy in this box. And for the sake of convenience, we can choose this potential energy associated with the particle to the box as equal to zero. So if we start with the Schrodinger's steady state equation, that is time independent equation, is del square upon h bar square E minus V of psi is equal to zero. Now this del square is a Laplacian operator. We know its structure. Our problem is only constrained towards one direction, and that is x. So in that case, we can replace this Laplacian operator by the total double derivative d2 psi upon dx2. There's no need of writing the partial derivative here because only x is changing in this problem. Plus 2m by h bar square E. It must be E only. E psi is equal to zero, because in the given problem the potential energy is chosen to be zeros. Here V is a symbol symbolizing the potential energy, so that is taken out to be zero. Now we can write down this equation like this: d2 psi upon dx2 plus alpha square psi is equal to zero, where this alpha square is 2m by h bar square E. So alpha can be written as under root of 2me divided by h bar. So we have a second order differential equation here, and its solution can be written in terms of periodic functions cos and sine theta, and that solution is psi is a sine alpha x plus b cos alpha x. Now this is my wave function, and I would like to use the boundary conditions. The very first boundary condition will be at x is equal to 0. At x is equal to 0, psi will also be equal to 0. Because in this equation I have unknowns. A is a constant, I don't know what it is, what is its value. B is a constant, I don't know what is its value. So to calculate these values, we can make use of the boundary conditions in this problem. So doing so, starting at x is equal to 0, psi is coming out to be 0. Psi must be 0 at this point, because we have assumed infinitely hard wall. So what will happen to this equation? You will get 0 is equal to a sine 0 plus b cos 0. Now sine 0 is 0, that means this is gone. So cos 0 is 1, so b will come out to be 0. So when b comes out to be 0, this term will be taken off. So what we will be left with a wave function psi equal to a sine alpha x. Now, the other part of the problem is that I want to calculate the value of a. I want to calculate what this a is. And this a can automatically be calculated by making use of normalization. So normalization can be used here. So using normalization. So how can I use that? That is line integral. Okay. Square of psi dx. So the limit of the integration will move from 0 to L. So the integral will be like this. Instead of psi, I will write a sine alpha x whole square dx. This must be equal to 1. This must be equal to 1. So a square can come outside of the integral. Okay, now you can have the limits from 0 to L. Now if you have sine square theta, that is equal to 1 minus cos 2 theta divided by 2. You can use this formula in this integral and its value will come out to be L by 2. So a square L by 2 will be equal to 1. That implies a will be under root of 2 by L. So the value of this a is under root of 2 by L. So what will the wave function look like now? The wave function will be psi is under root of 2 by L sine alpha x. Now let's move on and use another boundary condition. You see, at x is equal to L, what will be psi? Psi will be 0 again. So in that case, I will write 0 at x is equal to L. Psi must be 0 again. So psi is 0 is equal to a sine alpha L. It is alpha x. Instead of x, we will be using here L. So a is not equal to 0. We have calculated a. Its value is under root of 2 by L. So sine of alpha L is equal to sine of n pi. Because 0 can be written as sine of n pi. Sine and sine will be removed. What will we get? We will get alpha. So alpha will come out to be n pi by L. So this alpha can be used here in this equation. And we have got sine for n values is under root of 2 by L sine of, instead of alpha, n pi by L times x. So this is the wave function. See, this wave function has automatically come out as we have used the boundary conditions in the given problem, as we have used the boundary condition and normalization. So I should say the boundary condition and normalizations used in some specific problem, the problem of interest, automatically leads to the calculation of wave function. So this psi n is something like this. So we can plot the probability density of this psi, and we can plot this psi n as well. So if we plot the probability density of this psi n. We get results like this. So for n is equal to 1, it's something like this. For n is equal to 2, it's something like this, and so on and so forth. Yeah, it's looking so bad. So this is psi 1 square and this is psi 2 square. So this is the probability density for wave function in the state n is equal to 1. This is the probability density for the wave function for the state 2. Now you can see the maximum probability of finding the particle in the first state is at the middle. This is the maximum probability. And if you go in the same problem, then in the next state n is equal to 2. In the previous case, the probability was maximum at the center. In the next case, the probability of finding the particle in the same state is 0. You cannot find the particle at all at this point. So this is how the probability density is plotted for this wave function. And revealing the fact, it is as if the particle trapped in this one-dimensional box is equivalent to the standing waves that are formed by a rope which has been fixed onto walls. The probability density here seems to have a reference in standing wave problem. Now the next question here is energy. What will be the energy? So alpha has come out to be n pi by L. From here, what alpha is equal to? Alpha is equal to this much. So alpha, instead of alpha, I will write 2me by h bar is equal to n pi upon L. You can have scattering on both sides. 2me is equal to n pi h bar square divided by L. So what will be E, n? That will be n pi h bar square divided by 2mL. Are you see? Energy. The energy of this particle, if we take the classical consequence of a particle, being in a box or outside, it will have all possible energies. The particle will have all possible energies. But here, in a field where we have a microscopic particle in a one-dimensional box having infinitely hard walls, in this case, particle can have only some quantized values of energy. It cannot have all possible values of energy. So quantization is automatically coming as a result of solving the Schrodinger wave equation for the given problem. And what's that? You are finding here that this particle in a box, in a one-dimensional box with infinitely hard walls, will have only discrete values of energy.